Okay, so for the last section of notes for chapter 9A, so this is the first part of 3. So we are looking at area again. So when we have our area formula, so this is that area formula. So when we are finding the area of the inner loop of r equals 1 plus 2 cosine theta, it's very much like what we did with our polar coordinates, our area with our petals. So the first thing we want to do is we do want to graph it so we have a general sense of what it is that we're trying to find. So I have 1 plus 2 cosine theta, so this is going to be a limacone. And then our cosine is positive, so our values for cosine that are positive head to the right. And so I know in general, like I should have a graph over here on the right. And then I'm going to just do a t-table just so I have a general sense of what the quadrantals are going to do and how they affect this. So I'm going to just substitute in 0 first. So I would do 1 plus 2 cosine of 0. And so then I know that the cosine of 0 is equal to 1. And so then 1 plus 2 would be 3. So at 0, I would go out a distance of 3. So I would have a dot here. And then I'm going to go ahead and put in pi over 2. So that would be 1 plus 2. And then the cosine of pi over 2 is 0. So that would be 1 plus 2 times 0, which would be 1. So at pi over 2, I would be at 1. And then at pi, I would do 1 plus 2 cosine of pi. Cosine of pi is negative 1, so that would be 1 minus 2, which would be negative 1. So then at pi, I'm going to go away from the angle, and I would go back 1, so I would get a dot here. And then for 3 pi over 2, that would be 1 plus 2 times the cosine of 3 pi over 2, which would be 0. 1 plus 0 is 1. So I have that. So the limacone is kind of that heart-shaped graph. So it looks something like that. And then it has that inner loop. And so this is asking me to find the area of that inner loop. So what I'm looking for is what is the area of just that section here. So I know that when I'm graphing this, so this entire graph goes from 0 to 2 pi, so I just need to figure out, okay, what are the radial lines that would give me just the inner loop, right? So I would just be looking for, the alpha and the beta that would create those values. So just like we did with the petal graphs, it's going to start and stop at the radius is equal to 0. So then I'm going to just set that equation equal to 0 and then solve. So I'll subtract 1, divide by 2, and so then I have a reference angle, so theta prime would be at pi over 3. Sorry, I had to think about that. Okay. So then now I want to figure out, well, where is cosine negative? So cosine is negative on the two, quadrant 2 and quadrant 3, because cosine is my x value, and so it would be negative when I head left. So my reference angle is pi over 3, so then my rotated angles would be here at 2 pi over 3, and then again at 4 pi over 3. So my rotated angles, and so now keep in mind I'm getting negative ratios here, right? So cosine theta equals negative 1/2. So even though I'm looking here between 2 pi over 3 and 4 pi over 3, that's what I just solved for, all of those ratios are negative. So when I go along the radial line of 2 pi over 3, I'm going to be headed away from it, right? And so that's why that inner loop is, to the right of it. And so 4 pi over 3, same thing. I'm going to head away from it, and so that would give me that inner loop. So then the area would be just using that formula from above. So that would be 1/2, and then my lower limit is 2 pi over 3. My upper limit is 4 pi over 3. And then of r squared. So one of the things that students struggle with a lot is figuring out that alpha and the beta. So you can always, if you're unsure of what you just did, is graph it and kind of verify it. So that's what I'm going to go ahead and do. So I'm going to go into Desmos and we'll take a look at what will that look like. So let's first go ahead and just graph that. So we have r is equal to 1 and then plus 2 cosine, 2 cosine theta. And so there is that graph, and I'm on a coordinate system, but that's okay. So then now let's restrict it to what we think it is. So we thought 2 pi over 3, and then that would go to 4 pi over 3 here. And so if we look, it did just draw that inner loop. Okay, so that's one way for us to check that. And then I'm going to go ahead and copy and paste just this part so I don't have to type it in again. And then let's go ahead and find the area while we're here as well. So int, right, that gives me integration. And then we're going to go for my lower limit. So the lower limit was 2 pi over 3. And then our upper limit was 4 pi over 3. And then of our radius squared, and then with respect to theta. And so that gives us an area of 1.087. And so that would be that area. And let me put a little wiggle on there because that's an approximate. Okay, so that is, and then that's the only one I'm going to actually find the area for. The others I'm going to go ahead and set up so we can see that a little different. So, or save a little time. So we're just going to do setup only for the rest of these problems. Okay, so for this one right here, I want to find the area of the region that is common to these two functions here. So I'm going to use different colors when I graph them so we can kind of keep them separate from each other. So I'm going to graph this one here first. So r equals -6 cosine theta. So if I know what the graph looks like, you know, I would go ahead and graph it. If not, then I would do a t-table, right? So when I have this, I have when theta is 0, I would have -6 times the cosine of 0. And then the cosine of 0 is 1, so that would be -6. So let me go ahead and set up my graph. So when theta was 0, I would be out here at -6. And then for pi over 2, that would be -6 times the cosine of pi over 2. Cosine of pi over 2 is 0, so that would just be at 0. And then I would get that repeated pattern all the way around. So I know that this is a circle, or some people think of it as like kind of a single petal. Let's try to clean that up just a little bit here. That's going to erase that whole piece. Okay. And so what I'm looking at is, so where is cosine negative? That's over here. And then it's kind of like a single petal, right? So 1 theta, so a petal with a length of 6. And so that really is just kind of a circle that would head to the left. So then let's go ahead and do the second graph. So again, I have, if I need to, I would do a t-table. So I'm just going to use a space and then I'll erase it in just a minute. So when theta is 0, I would have 2 minus 2, and then the cosine of 0. Cosine of 0 is 1, so 2 minus 2 would be 0. So that would be here at the pole. And then if I put in pi over 2, I would get 2 minus 2 cosine of pi over 2. Cosine of pi over 2 is 0, so 2 minus 0 would be 2. So that would be somewhere, let's say right here. And then at pi, how about here at pi, I would get 2 minus 2 times the cosine of pi, which would be, 2 minus 2 cosine of pi. Cosine of pi is -1, so that would be 2 plus 2, so that would be 4. So at pi, I would go out to 4, so we'll say right around here is 4. And so then I have a graph that does that, and then I know because of symmetry, or you can substitute in the other points, I would get a graph that looks like this. Okay, so I'm going to need some space here, so let me erase this. So if you don't know your graphs, right, you're just going to substitute in your values. And so this is my circle, and this is what we would call a cardioid. Okay. So I want to find the area of the region that is common to the two regions. And so that would be this section that is in here, right? So that piece there is what I'm looking for. So I'm going to dissect this so we can make sure that we understand what it is that we're trying to find. And so this is one problem that a lot of students will struggle with. And so I want to find this intersection right here. And so when I find that intersection, I'm going to have this radial line and this one right here, right? And I'll just call this one alpha and this one beta. So if I look at those lines, so beta and alpha, so which I need to find here, I can see that this section right here, this is not to scale, is this section. And it is bounded by alpha and beta and the curve that is the limacon. So this curve right here is 2 minus 2 cosine theta. And I just realized I said limacon, but it is our cardioid. And so when I am finding that area, I need to first figure out, okay, well, what is the area of just that section between alpha and beta of 2 minus 2 cosine theta? But then I also have these little sections right here, right? This little piece right here that is bounded by the circle. So I still have those same radial lines, right? So I still have the beta. I still have the alpha, but then I have this piece right here. So this is exaggerated on the size of it. And I have this piece right here. And it's these two pieces together that are creating that shaded region. And so I am searching for, so I'm going to call these like, these are like little sliver pieces, right? And that's what I'm looking for there. And that is bounded by the graph of the circle, which is -6 cosine theta. So I have, 3 different pieces I'm looking for, right? So I'm having the main body of the graph, which is this one. And then I have these 2 tiny little pieces I need to add on to that. So in order for us to do that, we have to find those alpha and beta lines, which are really the same kind of line, right? So let's go ahead and do that. So how do I find where 2 graphs intersect? I just set them equal to each other. So I'm going to take that first function, so 2 minus 2 cosine theta, and then I'm going to equal it to the other one, which is -6 cosine theta, and then solve for that. So I'm going to add 2 to the other side, or excuse me, add 2 cosine theta to the other side, and then divide by -4. So -2/4 would be -1/2. And so then I just solved that on the previous problem. And so my reference angle is pi/3, and then cosine is negative in these 2 quadrants. So my 2 rotated angles would be 2 pi/3 and then 4 pi/3. So I know that this rotation here would be 2 pi/3, and to here would be 4 pi/3. And then for this particular problem, so I know again, so this is 2 pi/3 here, and this is 4 pi/3. So that part's not going to change. But I can't go from 2 pi/3 to 4 pi/3 because then I'm going to find something that isn't helpful. So I want to find just like one of these pieces. And so instead, what I'm going to do is I'm going to actually just go between the quadrantal and 2 pi/3 and then double it. So this quadrantal is at pi/2. So I'm just going to find the area of this one right here and then double it so that I include that bottom one. So then my area would be 1/2, and then the integral from 2 pi/3 to 4 pi/3 of this function squared, right? And then plus, and now I'm going to do double this. So I'm going to go 2 because I want to find it, for just 1 and then double it because of symmetry. So 2 times 1/2, and then I'll start at the quadrantal pi over 2, and then go until I hit that first radial line of 2 pi over 3, and then of my function, -6 cosine theta squared, and then d theta. Okay, so I just did the setup, but that would give me the same idea. All right, and then let's take a look at one more here. So I want to find the area of the region lying between the inner and outer loops of r equals 1 minus 2 sine theta. So let me go ahead and graph that. So for the graph, so I'm just going to go ahead and set up a t-table, get a few points landed, and go from there. So when theta is 0, I would get 1 minus 2 times the sine of 0. Sine of 0 is 0, so that would just be 1 minus 0, or 1. So then I would go out to 1 unit. And then let's do pi over 2. So that would be 1 minus 2 times the sine of pi over 2. So at sine of pi over 2, that would be 1. So 1 minus 2 would be -1. So then at pi over 2, which is here, I'm actually going to go -1, so 1 unit away. So that would be there. And then at pi, I would get 1 minus 2 times the sine of pi. Sine of pi would be 0. 1 minus 0 is 1. And then we'll do 3 pi over 2. So that would be sine of 3 pi over 2 is -1. So that would be 1 plus 2. So that would be 3. So we have another limacon. So we have kind of that heart shape and the inner loop. And so we want to find the area that is in between the inner and the outer loops. So we're looking for this section right here. Okay, so we need to find those radial lines again. So we're going to look for these 2 lines right here, right? And so that would be when the radius is equal to 0. So that's going to be my first step, is figure out when does it go through the pole. So I'm going to take the radius and equal that to 0. So subtract 1. And divide by -2. So sine is equal to 1/2 at pi over 6. And then I also want to find the quadrant 2, because it's also positive there. So that would be to 5 pi over 6. Okay, so then now I'm going to pull this one apart just like I did previously, so we can see what are the 2 things that we're looking for, right? So if I look at the section between pi over 6 and 5 pi over 6, so let's start with that. That would give me just my inner loop. So if I go from pi over 6 to 5 pi over 6. So one of the things I could do is I can say, all right, let me just find the area of the whole thing, right? So the area of the whole thing. And so that would be starting at 0 and ending at 2 pi. So then I can find this area, right? That total area. And then I want to subtract that inner loop piece. So if I subtract this part here, right? So when I look at that, I would have the area is equal to 1/2. And then if I do the whole thing, so from 0 to 2 pi of r, which is 1 minus 2 sine theta, and then squared. So that would find the total area. But then I want to take away the area of the inner loop. And so that was from pi over 6 to 5 pi over 6 of 1 minus 2 sine theta squared d theta. Okay, so we're not done with this problem though. Okay, so this problem involves a little trickery here. So one of the things that you have to keep in mind is that when this is drawing, okay, so when this is drawing out, so when I go from 0 to 2 pi, right, So when I first am drawing this, it's drawing this one section right here. And when it draws that one section, it's finding the area from the pole. So it's doing all of this, right? So it's finding that piece there. And then when I subtract the inner loop here, I have to take into account that this area is covered twice. So because that area is covered twice, once when it draws the outer loop and once when it draws the inner loop, I actually have to subtract 2 of those inner loops. So what I'm saying here is that if I were just to draw the outer loop, this area exists, right? Isn't that area there? So because I'm looking at the whole thing, so that area is there one time, when I go and pass over it a second time, it creates a second layer. And so that second layer has to be subtracted as well. So I have the area that exists. Whoops, I didn't want to draw that. Let me do that again. Okay. So I have to take into account that if I were to just look at that piece, that area is still there. And then when the inner loop is drawn, that creates another layer of area. And so that means I have to subtract 2 of them. So if I take the lazy road, so to speak, of just saying, okay, let me find the total area first, so the 0 to 2 pi, then I have to make sure that I'm taking into account that that area was created twice. And so I have to subtract 2 of them away. One thing that I could do instead, if I don't want to, go to that trouble, is I could say, all right, well, then instead of, going from 0 to 2 pi, I'm just going to go and find the area of just when it draws the outer loop and then subtract just when it draws the inner loop. So I could do that instead. And so what I would have to do then is I would take a look at when it finished drawing the inner loop, which is at 5 pi over 6, right? So that would start me here. And then I would go from 5 pi over 6 and then go around and finish. And then I would do that by not stopping at pi over 6, right, because I'm going past it, but I would have to add the 2 pi to that. And then that would be 13 pi over 6. Okay, because pi over 6 begins the inner loop. And so then I would finish the outer loop 2 pi radians later, so pi over 6 plus 2 pi. And so I could change the limits of the first one, and then that would draw just that outer loop. All right, and that is